Hey guys, so as promised, let's start off with Andrew Ng's Introduction to Machine Learning course. Now, this is a course I took in, I'd say mid 2017, during a university break, and I took the course at the time not really thinking that I was going to pursue machine learning. I didn't really know what machine learning was about. Um, I did it just really for the sake of learning. So some of the mathematical rigor, some of the programming rigor, and even some of the theory did escape me at the time. But I think this is a really beginner-friendly course in that Andrew, he's a fantastic teacher and he makes it accessible to quite a few people, a really broad audience, by essentially um, taking some of these things, some of these more rigorous elements that you might not use in your day-to-day, and just sort of leaving it out or making it um, a bit less important to the rest of the course. So actually, if you're struggling with mathematics, if you're struggling with uh, the more technical side to machine learning, especially the low level stuff, I think Andrew Ng's a fantastic teacher, and his teaching style really allows you to uh, essentially thrive. So he started off back then trying to define machine learning to us, and he presented two definitions. Let's see if I can bring it up. I had this one prepared just earlier. Um, so the first one is by this guy called Arthur Samuel, and he sort of said in 1959 that machine learning is the field of study that gives computers the ability to learn without being explicitly programmed. This is a older definition. It's a bit of a broader definition, but actually this is the definition that I would probably lean back on. It's not the best definition out there, but I think it's the one that best explains what machine learning is to new people. Um, there's another one that's a bit more rigorous, a bit, I guess, more bound, by this guy called Tom Mitchell, who came up with this one in, what, 1998? I've got that down in my notes. And he sort of said a computer program is said to learn from experience E with respect to some class of tasks T and performance measure P if its performance at tasks in T, as measured by P, improves with the experience E, which definitely is true. Um, this is very nice. The person that's written this has given us an example here. But I think this is something that you'll find is really prevalent in machine learning, that a lot of the information that's provided to you, while it might not be wrong, can be initially very confusing. And it's because it's phrased in a certain way that if you don't have the right mindset when tackling it, you won't actually be able to grasp the abstractions or the what the original author was getting at. And this is something that I think we'll experience as we go along. So following this, you sort of went down into the different types of machine learning. At the time, we looked at maybe three types of machine learning. Now it's more commonly accepted that there are four. Back then it was, supervised learning, unsupervised learning, and reinforcement learning. Um, reinforcement learning was some real hot shit back then, I have to say. Uh, so supervised learning, this is probably the more standard machine learning that you'll um, encounter, especially in your first few projects. This is essentially just finding, predicting rather a variable from some past data that you have. Unsupervised learning is trying to learn patterns and data, trying to do things with data without any explicit input, any of your own input. Um, Reinforcement learning is kind of the same as unsupervised learning. You're not really uh, manually putting in labels, but you're rather relying on a system, like whether that be a world system or like a physics simulation, to provide that sort of input back to the model. And semi-supervised learning is something that's really exploded in the past few years, especially with the rise of transformers. So that's basically what things like, GPT-3 and BERT and the Claude models, that's what they rely on, semi-supervised learning. Uh, so next up in my notes, I've got some more information on supervised learning. So we've got regression, which is sort of predicting a continuous uh, valued output, e.g. a house price. That's a really common first project that people have, house price prediction. Um, and regression sort of looks like this. Let me see if I can bring up regression. I'm going to open up classification as well because we're going to be talking about that next. So regression sort of looks like this, where you have this data here and you don't have this line. You first sort of make an assumption about what this line is going to look like. Normally you start with the simplest case, in this case a linear line, and you sort of try to figure out the variables that make this line the way it is, right? So if you go back to maybe, I don't know, intermediate or high school mathematics, you'll know that the equation of a line is y equals mx plus c, where m is the gradient and c is the intercept. So to put that in machine learning terms, you have y equals theta 1 x plus theta 2, where theta 1 is the gradient and theta 2 is the intercept. With this data, you're trying to figure out theta 1 and theta 2, the parameters, to make this the best fit that it can be. Now, just because this is linear now doesn't mean it will always be linear. You might have a situation like this where this is obviously not a linear line. The line of best fit is going to have a curve in it. And to introduce that curve, you're going to need something like a x squared term. And with that, you'll need another parameter. Now, I've written down here that in supervised learning, we already know what our correct output should be, as we have an idea of the relationship between the input and the output. In regression, we attempt to map input variables to some continuous function. That's y equals theta 1 x plus theta 2. In a classification problem, we try to map input variables into a discrete category. So in classification, maybe it's easier to sort of just think of it as putting your data points into buckets as opposed to, plotting out a line like this. Really, you just get data points and you're trying to say, well, this is blue, this is green, this is whatever. Maybe this is going to bucket 1, this one's going to bucket 2, essentially. And then we have unsupervised learning. There's a few forms of unsupervised learning. We've got clustering. That's a really, really popular one. Clustering is basically focused on, well, as the name implies, creating clusters of data points based on the structures and patterns that already exist in the data. So that's trying to get the data to sort of self-organize itself using an algorithm. And we have non-clustering algorithms as well. The most famous example I can think of right now is PCA, Principal Component Analysis, which is a pretty popular statistics tool as well as a a very simple machine learning tool. Some unsupervised learning, I've put down here that unsupervised learning allows us to approach problems with little idea of our results. Structure can be derived from data where we do not know the effects of the variables. So that is to say that you don't know what the effect of one variable will actually have. You have this data, you don't know what it's doing, you don't need to know what it's doing, but you can find structure anyways. So structure can be derived by clustering data based on relationships among the variables in the data. That's what I was explaining earlier around clustering. And then up next, I've got some, I guess, some more mathematical, I wouldn't say nomenclature, but maybe symbols, things that we should be familiar with. So M, that's a term that's commonly used to denote the number of training examples. You have xi and yi, which looks something like let's say you have x2 and y2, it would look like this, x2 and y2, right? And I is, in this case, denoting the ith training example, and I will go from 0 up to n, right, your total number of training examples. I've got a little picture or a little self-drawn diagram of what a supervised learning process should look like, but I don't think I need to show you that because we'll find much better ones later. So I've then written that essentially, oh, okay, I see where this is going. The next part that we're sort of looking at is the cost function. And this is also known, well, it's not the same as the loss function, but these two are sort of used in the same space, right? The cost function is an estimate over basically the error that that you're getting. So if we take a look at this written out, it's going to look like so J, our cost function of theta. Gosh, where's theta? It's theta, right? No, theta. Why do subscript? One. So hey guys, I'm coming in post-production here because unfortunately my mic audio just cut out. Essentially I got tired of trying to type up the equation. I realized I couldn't really do it. So I decided to go to the video that Andrew Ng has. This is a video that someone else has uploaded, which is a combination of all the lessons that he used to put up. Essentially, what we're looking at here is the loss function. So we're trying to minimize this to essentially do machine learning. And this starts with this term in the middle here, h naught xi minus yi, which is essentially saying our prediction for xi minus yi, that's our error. We're going to square this error to make sure that it's always positive, and we're going to sum it for all cases of I from 1 up to m, where m is all of our training examples. We're averaging this by dividing by m, the total number of training examples we're summing over, and we're going to add a 2 in the front to make the maths in front easier. More formally, this is known as I think a loss function. Let me just double check that. The cost function, rather. And unfortunately my camera is going to be covering part of the screen where it shows you that cost function more formally, but I think I'll show it in just a minute. Unfortunately that's going to be a common occurrence over this video. So over here I'm just talking about the whole, like the function itself, the summation over I from 1 through to m, and that 1 over 2m over there. And we're trying to minimize this here. And this here is basically a more, I guess, intuitive look at what I mean by minimize. This is starting to allude to something called gradient descent, which is a very fundamental principle in machine learning. So over on the right there, those are the data points that we have. They're quite simple data points. You know, you've got 1, 1, 2, 2, and 3, 3. Those are our 3 data points. And we're trying to find a line y equals mx plus c that fits those data points. In this case, we're making the intercept 0 to simplify the mathematics to sort of show what's going on a bit easier. Um, so if you had a gradient of 0, which is currently being shown in the video, you'll find that your cost function, if you do the calculation for every single point shown earlier using that equation, will turn out to be something like 2.3, which is what Andrew has done. It turns out that if you then make your cost function 0.5, so you have a slope of 0.5, that cost function ends up being a bit lower because the difference between your points and the line prediction, or your points and the line ends up being much lower. And it turns out if you make your slope 1, then if you make theta 1 equal to 1, then your loss is actually 0 because your points fit perfectly on the line and you've reached the global minimum in this case. And that parameter, the parabolic function on the right there, j of theta 1 with respect to theta 1, that's the loss, not the loss curve. It's I forget the exact definition, but basically that graph there is very important because we're going to use that to demonstrate how gradient descent works in a bit, which is essentially where you pick a few random parameters. In this case, it will just be a random theta 1, and then you'll calculate the slope, and you'll walk in the inverse of that slope to try get to the local minimum. And the way you normally do this is you do this iteratively, which we'll cover also in a bit. I'm not sure what else I'm talking about here. I'm sure it's quite important, but unfortunately I've got the memory of a goldfish and this content is escaping me. Let's see. Excuse me. I think here I'm talking more about gradient descent and how the derivative of that function with respect to theta 1 is going to give you your gradient. So if you're familiar with derivatives, that's fantastic. If not, that's something you should get up to speed with. But basically, it's just finding the slope of that line at a particular point. And here I've realized again that my camera is covering up some important part of the graph. I think here I'm walking through like each of the examples. Like in the case of theta equals 0, then your error is 1 squared plus 2 squared plus 3 squared because the predictions for each point will be 0, 0, and 0, and the actual value will be 1, 2, and 3. In this case, it would actually be -1, -2, -3, but because of the square, it becomes positive. I don't think Andrew's written that because, it doesn't really matter at the end of the day. When you square it, it all becomes positive. Okay, here, and we've moved on to a graph that I think better shows the idea of gradient descent. So what we're doing here is we're looking at two equations, um, or rather one equation written down two times, each for the partial derivative of theta 1 with respect, sorry, the partial derivative of the cost function with respect to theta 1, and essentially where it says theta 1 dot dot equals, that's an assignment. So it's saying the next theta 1 is going to equal the current theta 1 minus alpha times the partial derivative of that cost function. And essentially what that's saying is, the error in that cost function, the partial derivative of that with respect to theta 1 is how much theta 1 has contributed to that error. So we're going to walk our um, thing back that much. So in the case of the top graph there, you've got a excuse me, you've got a slope that is positive, the positive slope being the rise over run, the rise being a positive number since you started off at maybe 1 and you end up at 3, and then the run being, I don't know, like 2, it doesn't matter. What he's trying to illustrate here is the positives and negatives. So that gradient is going to be positive, so that is to say that blue box will be positive, and because you have a negative alpha in front, what happens is you'll be moving in the opposite direction, so your theta 1 will be moving towards the local minimum, um, which is a smaller number than what it currently is. And in the bottom one, you've got a negative slope because your run is going to be negative, which I'm indicating here. So your rise is going to be negative, and your run is going to be positive, so that will be a negative number. And again, when you multiply by that negative alpha, what's going to happen is you're going to be moving forward because your theta 1 plus alpha will be positive. And in this case, we're talking about the learning rate. So realistically, currently, learning rate isn't something we need to worry too much about. You just need to pick an appropriate number. If you pick it too small, it's not actually too big of an issue right now. Your gradient descent is just going to be very slow. It's going to take probably more time than it really should be taking. But you'll reach the local minimum anyways. This is a simple example. Sometimes for more complex ones, you're more likely to stay in a local minimum if your learning rate is too low. But similarly, if your learning rate is too large, then you're going to have some very big issues as well. I'll just wait for me to scroll down. But essentially, if you imagine the same graph and you want to make an adjustment, if your learning rate is too large, then it will overshoot the local minimum, and it might even end up on the other side, but much further up. And then, when you try adjust it back, then again it will be further up again, and then you can sort of shoot yourself out, as shown in this graph here. And this is going to cause an issue, as it will create your model will never converge on the local minimum. In fact, it will diverge, which is what he said there. Here, Andrew is just talking about the importance of simultaneously updating everything. You don't ever update these things independently. It's really weird. It turns out when you do this in code, although the math looks complex now, it ends up being really simple, and it's quite computationally efficient to simultaneously update everything normally. If you do it one at a time, then it's going to create issues, because what's going to happen is you're going to be doing partial derivatives with respect to parameters that have already been changed. Sorry, not with respect to parameters that have already been changed. You'll be doing it with parameters that have already been changed, which will cause some issues. Might still work at the end of the day because it's an optimization algorithm, and maybe the effect won't be that large, but it's fine. Yeah, let's see what the next slide is. So we're moving back. I think we're going to talk about local minimums here and global minimums. So we've only really looked at cases where there's one minimum, but in this case, um, you can have a local minimum that isn't the global minimum, and this is quite common. In fact, this is the most likely situation that you'll get in your machine learning problems. You'll have cases of local minimum and cases of global minimum, one global minimum rather, and you're trying to get to as close to the global minimum as possible for your loss function. There are ways to get around, um, or to, sorry, there are strategies to avoid being stuck in the local minimum or to even reach the local minimum, but we'll cover that much later, and they're mostly around the gradient descent algorithm. So I think here I'm trying to find the equation for um, the derivative because I think that's important for us to understand. This is something that will come up much later, these equations around partial derivatives with respect to um, each individual parameter. With something like this, it turns out that well, it gets hard before it gets easy, but when it gets easy, it's actually really elegant and quite beautiful. But, for this equation, um, when you pull it out and when you do that partial derivative with respect to theta naught and theta 1 as shown in the bottom there, which my screen camera is covering again, um, it turns out to be for theta naught, the partial derivative of the cost function is 1 over m summation of the internal function over I from 1 to the total number of training examples you want to calculate. In this case, we calculate them all, so it's m, and the internal function is what we've expected previously, which is our predicted value h naught or h theta x of I minus the actual value of y of I. And with respect to theta 1, it's pretty much the same. The reason why we added that 2 here becomes obvious because when we do the chain rule and when we do that squared, the 2 comes out and it cancels with that 2 we put in earlier. In the bottom case, we have an xi as well on the right hand side because when we do the derivative of theta 1, you get xi because that is the coefficient there for theta 1. But for theta naught, there is no coefficient. The coefficient is 1, so you multiply by 1, you don't really write it down. And the final thing I wanted to cover is that, or that Andrew covered for this week, is that what we've been looking at so far is a batch gradient descent. Then that is to say that we're using all the training examples, and that's evident when we do the summation over for I going from 1 through to m, which is our total number of training examples. There are other forms of gradient descent. We'll cover them later, but realistically, once you understand, batch gradient descent, the other ones aren't too complicated. Cool. And that's it for this video. So this has covered week 1 of the Introduction to Machine Learning course by Andrew Ng. Really, it's covered some of the basics, but probably the more important fundamentals, particularly around the mechanism around gradient descent. Cool. But yeah, so that's it for the first week, and my mic is working here. I hope you've enjoyed.